Hello everybody, my name is Brian and I'll be giving a presentation on three fundamental machine learning and data science tools in Python. The libraries I'll be covering today are Numpy, Pandas, and Matplotlib, and even just a basic understanding of each can help you use high-level tools more efficiently. The first library we'll be discussing today is Numpy. Numpy stands for Numerical Python, and as that would suggest, is a Python library for numerical operations. It implements a vectorized array and mathematical functions, including a set of linear algebra operations. Numpy is integral for almost every scientific and mathematical application of Python, mostly due to its very efficient implementation of multidimensional matrices. This is especially important for machine learning libraries where their linear algebra rules are used to speed up training models. Numpy expands on Python's data types in order to support a wide range of mathematical functions. Most of the time, Numpy is pretty good about operations between them, but sometimes a type mismatch can be a huge problem, such as if a machine learning library is being given data types that it wasn't trained with. So be careful about what data types you're using. The most important thing that Numpy adds are its arrays, the ND array. These extend heavily on the functionality of Python's base arrays with greater support for multidimensionality, indexing, and other operations. I'll be switching into a Google Colab notebook to demonstrate, so you can create a blank one or use the finished notebook in the description as reference. So, after you've installed Numpy, you have to import it into your file to use its functions. It's typically imported as np to save time while typing it out. Here's a quick demonstration of Numpy's data types. We can create a 16-bit int like this, or a 32-bit float like this. To create an array, we need some data for it. We can create one from an iterable like a list or a tuple. And if the iterable is properly formatted, Numpy will automatically recognize it as a multidimensional array. If we want to, we can specify a data type using the dtype argument, or convert it later using a function. Oh, I mistyped that. If we have a more general idea of what we want our array to look like, we can use some of NumPy's built-in functions to generate it. For example, we can create an array full of ones or zeros of a specific size using the ones or zeros function. If we want to copy the shape of an existing array, we can use the ones like or zeros like function. If we want to make an array of a range of numbers, we can use the arange function, which works a lot like the range function in base Python. If we want more granularity, we can use the Linspace function, which gives us far greater control over the numbers generated. It takes a start argument, a stop argument, and an integer number of increments between them. So if I wanted to make an array containing every number between 20 and 30 inclusive, I would do it like this. Now, for indexing arrays, there's a lot of new functionality. Let me make an array to demonstrate. We can still do single indexing, just like in normal iterables. We can also do slice indexing. We can even use list slices to get multiple single elements. Now, if we make a multidimensional array, then there are some new options that aren't in base Python. We can separate slices with commas to slice different dimensions of the array, like this. We can even index using these slices. So as you can see, the middle item was turned to 3. Of course, these arrays are built for math, so most Python operations support them natively. Let me make a few arrays to demonstrate. If we wanted to do an element-wise addition, multiplication, or subtraction between the elements, we could simply do it like this. If we wanted to raise the individual elements in an array to a power, we could do it with the np.power function. And if we wanted to raise e to the power of each element inside an array, we could use np.exp. We can also do scalar operations which affect each element of an array. For example, if we add the scalar 1 to an array, each element will be incremented by 1. And the same works for multiplication and all other operations. This is a subset of a more complicated aspect of NumPy called broadcasting, so I'll leave a link for official documentation for more information. And of course, there is the entire linear algebra suite of NumPy. Again, I'm not going to cover every operation, so there will be a link. For example, here's a dot product implemented with the out operator, and also a transpose. There are also some more general array functions, such as one for summing all the values of an array. Or changing its data type. We can also get the shape of an array. Or we could reshape it. We can also combine arrays with stacking functions. If your arrays have the same number of columns, you can vertically stack them. And if they have the same if they have the same number of rows, you can horizontally stack them. If you have two arrays with more than 2 dimensions, you can stack them across a single axis as long as all of their dimensions are the same. So axis in this argument refers to the 0-indexed axis of the dimension that is being stacked upon. So those are the basics of NumPy. Depending on the exact domain you're using it in, there will be more relevant information to you, but I think this is a good base for most applications. The next library I'll be discussing is Pandas. Pandas is named after panel data, which is observations of the same individuals over a period of time. Pandas is a data manipulation and analysis library built on top of NumPy and is optimized for working with extremely large datasets. The core elements of Pandas are its series and data frames. They act like NumPy arrays and Python dictionaries at the same time, but implement lots of new tools to analyze and modify the data within. They can also be created from many sources, including NumPy arrays, comma-separated value files, or even SQL databases. Now, I'm going to switch back to the collaboratory to demonstrate some of the basic functionality of Pandas. Like NumPy, Pandas is usually shortened to PD when importing it. This is a series. It's the lowest level Panda object. It's basically just a 1D NumPy array with more functionality. You can create them from a base Python array like that, or a NumPy array. You can also specify the indexes you want to use as a second argument. As you can see, Pandas keeps track of the indexes and the data type of the series. Now, a data frame is a collection of series as a single object. You can create them from a dictionary where the key will automatically name the series, and the data will be indexed with numbers if no arguments are provided. If you have indexes specified in one of the series, the other series will match it. So as you can see, even though the 2 series didn't have a fourth item, it was still automatically filled in with D. You can also insert columns into a data frame using the insert function, specifying a column index, name, and data. Oh shoot. Yeah. I never saved the data frame. Okay, that fixed it. And as we can see from this last column, the data types don't have to be the same across the entire data frame, but they should be the same inside of a single series. Of course, we can also import previously saved data from a CSV or comma-separated values file. You can also import one from a SQL database, but that's a little outside the scope of this presentation. The file can either be local or from the internet. Now that we have all of this data saved in a data frame, Pandas gives us powerful tools to analyze it. We can turn it into a NumPy array for further use, or we can look at the first or last few elements. We can also tell Pandas to describe our data frame for us. And if we just want one of those values, we can use another function. We can also sort by a specific column, which we can specify by index or name. And keep in mind that all of these operations actually return another data frame instead of modifying the data frame, so keep that in mind. If we want to look at a specific column, we can use indexing. Indexing is extremely nuanced, and you could probably make an entire career out of indexing large datasets, so I'm just going to briefly cover it. Much like a dict, you can access a specific column by name with a bracket operator. You can also index rows or specific entries with a slice operator. Pandas also implements NumPy-like array slicing through 2 operators, .loc for named columns and .iloc for integer index columns. You can use them like this. And yes, those are brackets after loc. You can use integer loc like this. So as you can see, .loc uses the actual names of the columns, while .iloc uses the indexes of the columns. Now, where it really gets complicated is conditional indexing. You can use Boolean operators on a data frame to get a Boolean map of which elements to grab and combine them using an ampersand or pipe operator. Here's a basic example. So this returned every element in the data frame which has an MPG of greater than 20 and a weight greater than 3500. And this ampersand is the AND operator, and the OR operator is the pipe. So this returned every element in the data frame which either has a weight of greater than 3500 or a weight of less than 1800. Pandas also implements functions to modify your data. There are .add, .sub, .mul, and .div functions, which do exactly what they sound like they do. If you're using Pandas to do lots of data crunching, you should install the libraries numexpert and bottleneck to speed that up. I'll type them out for you here. They will also be in the finished notebook for reference. Pandas also has handling for null values. Null values are expressed as np.nan. Among other things, you can choose to ignore those values completely. So you'll see that before, where the total number of rows was 398, it has dropped to 385 because we chose to completely ignore any values that have a null value. Remember that most data frame functions return a copy of the data frame with the changes instead of modifying in place. You can use the in-place argument or simply reassign the value. So as we can see with the in-place argument, the data variable has actually changed. If you want to save your data, you can use the .toCSV function. If you don't specify a file path, it will just output it as a string. There's a lot more to Pandas than what I've covered, including support for time series, which are basically panel data, and data frames beyond 2 dimensions. But Pandas is far deeper than Numpy, so this is all I can realistically cover in an intro video. Finally, we have Matplotlib. Matplotlib is a library for creating and displaying graphs in Python. It's based loosely on MATLAB, with support for bitmap display, 3D graphs, animations, and more. It also integrates very well with GUI applications, as we will see with Google Colab, which is basically just a Jupyter shell. The key components of Matplotlib are figures and axes. These are objects that describe a graph image together. This object-oriented approach is very Pythonic and allows you to create and visualize a large number of graphs. It is built on top of Numpy and integrates very well with Pandas. The main graphing interface is matplotlib.pyplot, which is usually imported as PLT. To get the default figure and axis, we can use pld.subplots. Right now the graph is empty, but we can fill it with some nice data. Oops, I forgot the NP in front of that. The plot command uses the first argument for x values and the second argument for y values. An optional label argument can be used to name the line. The line is also returned from the function in case you want to modify it further. So as we can see, a nice linear line. I'll add some more functions for reference. So as we can see, a quadratic and a cubic curve were added. You can use the setTitle function to give your plot a name, and the .legend function will create a customizable legend. Here, it'll just use the labels of the lines to create a nice legible legend. So I guess I accidentally ran one of the functions twice, so linear is shown twice in the legend, but if we want to clear the graph and start over, we can use ax.clear. And let's make a new graph. We can specify the appearance with the third argument in plot. So that argument means red dots. There are a lot of choices for formatting, so a link to official documentation will be included. We can also use functions to change the appearance of the coordinates. We can set the horizontal and vertical axes like this. So as we can see by the argument, the x-axis was set between 0 and 6, and the y-axis was set between 0 and 20, like this. And of course you can also change the increment and the number of increments, but that will be in the official documentation. If we want to, we can also give the axes labels like this. We can also combine multiple plots at once using subplots. To clear the whole figure at once, we can use this. Let's make some data to graph. Now to create subplots, we can use the subplots argument once again on the figure. It will return each subplot individually. And we can address them individually like this. So as you can see from this graph, they share an x-axis because of the sharex argument. Matplotlib has many built-in graph types, which play nicely with various data you may have from Pandas. And if you want to add some text to your graph, you can do so using the plot's own coordinates to place it precisely. So as you can see, it's displaying the mean, and it was placed at 3570. Matplotlib also has support for displaying bitmap images through representations as Numpy arrays. So just like Pandas, there's a lot more to Matplotlib than I've covered here. And you could also probably make a career off of making data visualizations in Matplotlib. A library I'm pretty fond of for making nice graphs is Seaborn. Of course, everything will be linked in the presentation notebook. And that concludes this workshop. I hope you learned some things about these tools that will help you with your future data science and machine learning pursuits.